way better than atmospheric relationship in terms of living material. We're seeing the acidification, and I guess you've been following those issues, right?
What were you saying?
Carbon dioxide dissolves really easy in water. Comparatively, it's accessible, so it has a chemical effect on the oceans, which is affecting the ability of animals to put down carbonates in the form of coral and shells of any kind. So moving the acidity, moving it towards a lower pH, higher acidity, makes it more difficult for coral reefs to build the corals. And if we didn't have so much ocean, 70% ocean on this planet, the effects of global warming and carbon buildup in the atmosphere would have been much, much higher. The ocean has been the buffer. More than anything else, the ocean has been buffering us, absorbing that carbon. And I've been wondering for 10 years, what's going to happen? What does that mean? You know, is there when the tipping point, or whatever you want to call it, that threshold gets reached where the ocean can't absorb that carbon anymore, what will that look like? And I guess one of the first signs is the changes in the coral reef. That's the most amazing handle there. It looks. I keep getting distracted by the shape.
It's flexible, so it can be
That's cool.
clamped anywhere.
I look back and forth in the crowd, and every time I come to that, I'm like, "What is that? That's wild." Anyway, any questions at this point? You can see quite an opening here. This tree's come down. Anybody, an enterprising person, counted the rings yet?
Oh. Yeah, there's only 25 on that.
553.
Oh, right on. You getting the word for that. The fastest counter. Anyway, have a look. You can see the rate of growth as well as the total number of trees.
The rate of growth is not very fast.
No.
That's what I've concluded here.
So have a look at the middle part.
Well, here it grows much quicker.
For the first 25 years, I guess, 25, 30 years, that tree is growing really fast. There's like 6 rings per inch, or whatever that is to centimeters. I'm still on inches on that. Most things I'm in centimeters. Let's see. I don't have the same. Doesn't look the same. So there's a difference. Is it? Really? You had me wondering. Because it looks quite different, doesn't it? Yeah. Maybe it's just the rot has made it hard to read.
Perhaps.
But this looks very clear from here in. First, not even 20 years, I guess. Rapid growth, and then it's starting to slow down. And by the time it's at the age of 30, 40 years, it's come down to a very, very steady sort of 10 rings per centimeter. But even at that slow rate, there's something that a forester showed me down island, and I love it. It's a tree puts on more wood, sequesters more carbon when it's big than when it's small. And you can tell because the rings are about the same size, width across, but the total circumference of that circle is bigger. So as it goes like this, it's growing the same rate, it seems to be, in terms of adding linear diameter, but because the circumference is bigger, it's sequestering more carbon and more carbon and more carbon as it's getting bigger, until it gets out here. And then it starts to really slow down. It's going, okay, like I weigh whatever tons, I don't know how many tons does a tree like that weigh.
It's a bit different. It's a sort of S-curve at the very start. When it starts growing, it sequesters more.
Right.
And then it follows an S-curve, goes this way. So as it grows older and older, it will sequester less. But it will have something which is fixed, which is already there when it was growing. So that's there.
I think are you interested in a dialogue on this?
Yeah.
My guess is what you're describing is the carbon sequestration per area.
No, process as it grows when it's new.
Per tree or per hectare?
Per tree. It follows a sort of S-curve.
All right.
So when it's growing initially in this period, it will sequester more carbon.
Okay.
And when it reaches a stage, a certain age, it stops sequestering a lot of it.
Okay.
It reaches a sort of plateau.
All right.
Well, I was saying that when it was young, though, it was actually not. It was a.
But if it's a S-curve, what type of?
Initially, it will sequester more, and when it's around 20, 30 years old, it sequesters more for 50, 60 years. I'm not talking about this particular species, but generally,
in general,
it follows an S-curve. So in this particular tree, it might be even that initial phase might be higher.
Okay.
That depends.
And I don't know either. I don't have the hard data for you, so it's interesting what you're saying. I know that when I've read papers on the subject, I've seen it often interchangeably used and confusing that if you measure per tree versus per hectare, because when you have a small tree, you typically have a lot of small trees. So they're coming up fast, growing fast, sequestering carbon, not very much per tree, but there's 300 times more trees. Then you get into something that's really big. It's blocking out the light. No more small trees. There's only one or two trees, or whatever number, 10 trees per hectare kind of thing. The number of trees goes down, and the amount of carbon sequestration per tree goes up proportionately.
Per tree goes up, per hectare goes down.
Right. So, and I understand. So what you're saying is slightly different from what I'm saying. So that's interesting. Anyway, any other comments, thoughts?
Prabhat,
Yeah.
how did you know it?
I read forestry management.
Oh, okay.
That's another interview.
And there are so many of these things where it's hard. Like, well, a classic example is trying to understand efficiency in an agricultural system, or efficiency in ecology. What does that mean? So you can measure efficiency against hours. In ecology, we look at how much time does an insect need to collect its food. That's one way of measuring efficiency. Another way would be energy balance versus time versus. So trying to do this it's like people want a simple summation. Does it do it or not? And the answer always is going to be couched in definitions that need to be looked at very carefully to understand. So the Americans want to tell us that their corn growing or wheat growing system is the most efficient system in the world. It is per man hour. If you want the most efficient carbon sequestration or calorie producing system, go to Southeast Asia and look at their rice paddies that are worked by hand. You'll start to see the balance. They almost get as many calories out as they put in. Whereas in a corn growing system or a wheat growing system in Canadian or American, it doesn't really matter, you're going to see huge amounts of oil going in, so it takes more calories to produce than you actually get calories in the food. And that's the kind of questions that need to be asked, and I find really fascinating.
So does this imply that it's worth logging the very old trees so that we allow smaller trees to grow because their rate of
Then you're looking at only one problem. This tree will be housed to lot many biodiversity species. So if you are, then you're just looking at a small portion of picture, that CO2 only. There are not many issues.
Right.
So you can't trade off. This is not a trade off that you get a big tree and plant eucalyptus here. So you can't do that. Because
So I agree with Prabhat, there's a lot of issues. If you're just asking about the carbon sequestration, even then, okay, those clear cuts that we came through, or what they're calling, selective variable retention logging, which means clear cut plus 2 trees left standing, virtually clear cuts, what you're seeing is they're planting trees, the trees are coming up and possibly sequestering a lot of carbon, but there's a lot of dead wood on the ground. And you could, when you looked at that slope, what was the dominant thing you saw looking up the slope? Dead material, woody debris. All of that debris is now going into the carbon cycle very fast. As it warms up, the ants become more active, the termites become more active, fungus comes in, and again, what's the overall balance? Fast growth, but at the same time a lot more decay.
and once the tree is cut, all of the carbon sequestered is in the atmosphere.
Yeah, it was a carbon cycle.
Carbon cycle.
You can manufacture much furniture, a lot of furniture, keep it in your house, so you won't have dead wood. And,
Yeah, exactly.
Huh?
So
What do you think of it?
accumulate stuff, consume,
Exactly.
buy more furniture, folks, and sequester that carbon.
There have been no studies which say that the carbon remains sequestered in those woods, because over the time it again reaches the atmosphere.
Well,
Once it's cut, in the consensus it said, once it's cut, that means all of the carbon which was sequestered has gone to the atmosphere.
Been logged, and I hiked for half an hour, and every step I was taking was the color of red. It was a different soil than this. The whole hillside was just bleeding the soil down. And the shrimp boats can tell you, anytime you log a coastal ecosystem forest, the shrimp get wiped out because the shrimp beds at the bottom of the ocean are covered with mud in that area. And on and on and on and on. So look at the whole picture. And it's not a new story for you. I'm sure this is stuff that you've all been looking at before. Pardon?